students. We're going to go ahead and start today with a little bit of bell work just to review what we did yesterday, talking about describing transformations of parent graphs. So as you look at the equation, y equals x minus 3 squared plus 7, what parent function does that go with? Right, it's squared, so it goes with the quadratic parent function. Remember, that's a U shape. And all we're doing is describing the transformations. So what things did you notice that I added to the graph that's different from y equals x squared? Right, one thing I did is I minus 3. Remember, that tells us to move the graph 3 to the right, the opposite direction. And then the plus 7 tells me to go up 7 units. That's all you'd have to say on that one. 3 right, up 7. Next one, f of x equals negative 2 plus the root of x plus 4. This one is a square root function, so it's going to look like y equals the square root of x. What things did I add to that graph or that equation to make it what it is? Right, one thing I did is the plus 4, which tells me to go 4 to the left. Remember, it's the opposite direction. And the minus 2, since it's on the outside of the square root, tells me to go down 2 units. Last one, g of m equals the cube root of m minus 2 minus 1. This is a cube root function because it's got the cube and the root. So we know that looks like y equals the cube root of x. What things did I add to make it different? Well, one thing I did is I subtracted 2. Remember, that tells me to go right 2 units. And the minus 1, since it's on the outside of the root, that tells me to go down 1 unit. And you could sketch a graph of each of these, just knowing what the parent function looks like and knowing what the transformations I gave to you. We're going to go ahead and continue what we talked about yesterday with transformations of functions. This is section 1.6b, so continuation of 1.6. Remember, these notes are on Canvas. If you want to print them off, you should have also received a copy of them in class on Tuesday, so you have a copy to follow along. Recall, f of x plus d moves the graph d units up because it's on the outside and we're adding. The minus sign tells me to move d units down. I'll put these in quotes to show that that's the units down because of the minus. What if I put it on the inside of the function? Well, plus, we said you go the opposite direction, so we're going to go c units to the left. And if I put a minus there on the inside of the function, I'm going to go c units to the right. Because it's a minus, we go the opposite direction. Now we're going to talk about reflections today. When we reflect a function over an axis, we simply flip it over what's known as the line of reflection. This line of reflection today is going to be an actual axis on the coordinate plane. If you reflect a graph, which means to flip it over the x-axis, the y values are going to change their signs. You can see that right here, negative f of x. This is our y, and the negative out in front tells us to flip the sign of the y. If I reflect over the x-axis, you see that the negative is with the x, so the x values are going to change their signs. Let's go ahead and try an example. Graph y equals negative root x and state the domain as well as the range. I'm going to create a table just like we did yesterday, so you can kind of see what this graph looks like. X's and y's. My x's, I'm going to choose them specifically because you can't take the square root of every number, as we saw yesterday. So I'm going to choose some perfect squares, like 0, 1, 4, and 9. Y equals negative square root of 0 is 0. Y equals negative square root of 1. Well, the square root of 1 is 1, but I've got that negative in the front. Y equals negative root 4. Root of 4 is 2 with a negative in the front. And y equals negative root 9. Root 9 is 3 with a negative in the front as well. So now I'm going to graph it. 0, 0, 1, negative 1, 4, negative 2. And last one, 9, negative 3. And there's our graph. Okay, how does this compare, though, to its parent function, y equals the square root of x? Right, if we think back to yesterday's notes, the square root of x looked like this kind of function, something like that. Okay, so that's what our function looked like from yesterday. That function, though, how it compares, this one has a negative out in front, so I reflect it over the x-axis. And you can see that from my graph here. All I did is take the parent function, the green one, and flip it over the x-axis. Let's see how that affects domain and range. Domain, how far left? My graph goes from 0 to the left, off to the right at positive infinity. The range, again, it starts all the way down at the bottom at negative infinity and comes all the way back up to 0 with a bracket. So that's our domain and our range for that function. Again, the negative, all it did is take the graph, as we can see, and flip it over the x-axis. Let's try another one. Y equals the square root of negative x. So I'm going to put some ordered pairs again. Negative x. And there's my y's. I'm going to pick just some x values. Again, I'm going to be selective because it's a root. You can't take the square root of every number. So I'm going to pick specific ones. Negative 4, negative 1, and 0. Y equals the square root. Negative, my x is negative 4, which becomes just positive 4. The square root of 4 is 2. Y equals the square root, negative, then my x is negative 1. That makes a positive 1. The square root of 1 is 1. And y equals the square root of negative 0, which is just 0. The square root of 0 is 0. Let's graph it. Negative 4, 2. Negative 1, positive 1, and 0, 0. And that's what my graph looks like. Remember the parent function looks something like this. And this is how it's reflected. You can clearly see by my graphs. How does it compare to y equals the absolute value, or the square root of x? It's a reflection over the y-axis. Because our negative is on the inside of the function, it's reflected over the y-axis. If the negative was on the outside, like our last problem, it goes over the x-axis. Let's think about domain and range. How far left does my blue graph go? Goes from negative infinity, comes off to the right at 0. The range starts at 0, and then it keeps increasing and going up to positive infinity. That's going to be our domain and range for that graph. Let's try some more. Next one, y equals negative x squared. Again, I'm going to just put some x and y values in here. Y equals negative x squared. You have to be careful on this one because the negative is on the outside of the x squared. Negative 2, negative 1, 0, 1, and 2. Just use our normal ordered pairs that we like. Y equals, my negatives out in front. In place of my x, I'm going to put a negative 2 and square that. Negative 2 squared is 4, but because there's a negative out in front, it's negative 4. All because of that negative in the front. Y equals negative 1 squared. Negative 1 squared is 1, with the negative in the front is negative 1. Y equals negative 0 squared. 0 squared is still 0, times negative 1 is still 0. Y equals negative 1 squared is negative 1, and y equals negative 2 squared is negative 4. Let's go graph it. Negative 2, negative 4, it's way down here. Negative 1, 0, 0, 1, negative 1, and 2, negative 4. I'm going to connect my graph together. What parent function does this go with? Right, y equals x squared, which is that U shape we talked about yesterday. How does this graph that I just did compare to the parent function, which looks something like this? Yeah, something like that. How does that graph compare to the blue one? Right, you'll notice it's a reflected or flipped over the x-axis. Because of this negative in the front, it goes over the x-axis. Right here, you can see that it was clearly flipped over it. Last thing is domain and range. Domain, it goes forever to the left, forever to the right because of the arrows. My range dips down to the negatives because it comes down on both sides. The highest y value is at 0. So that is my range of my graph. Let's try another one that looks a little bit different. Y equals negative x squared. You'll notice the difference between this one and the last one we just did. The negative is now in parentheses. So let's see how that affects our graph. Again, just choose some ordered pairs. Negative x squared, and then y. Negative 2, negative 1, 0, 1, 2. And plug them in. Negative, negative 2 squared. Well, a negative and a negative make a positive, and 2 squared is 4. Negative, negative 1 squared. Positive 1 squared is 1. Negative 0 squared. Negative 0 squared is still 0. Negative 1 squared is 1. And negative 2 squared is 4. Okay, so be careful. On this one, the x is negative, so make sure you put the negative inside those parentheses. Let's go graph. Negative 2, 4. Negative 1, 1. 0, 0. 1, 1. And 2, 4. And connect my dots together. Okay, and that's our graph. Think about the parent function though. How does this graph compare to y equals x squared? Well, that's what y equals x squared looks like. So did it change at all? No, it really didn't change a whole lot. But what happened, because of the negative on the inside, this graph is reflected over the y-axis, which you can clearly see by the red line. If I fold that graph and flip it over the y-axis, they do match onto themselves. And that's because of the negative in the front with the x. So if the x is negative, it's over the y-axis. If the negative is out in front of everything like it was on these previous examples, then it's over the x-axis. Let's talk about domain and range on this one. Domain, how far left? Well, it's got arrows, so it goes to negative to positive infinity. Range goes from 0 to positive infinity. Starts at 0, keeps going up to positive infinity. And that's reflections on parent functions. Let's go and talk about how you can stretch and shrink functions. And all of this depends on the value that's in the front of your equation. So whatever number it comes in the front. Vertical stretches. A vertical stretch occurs when the number in the front, the absolute value of it, is greater than 1. And it results in the graph being tall or narrow. So if you think about a rubber band, right? If I give you a rubber band and stretch it, it's going to stretch vertically. And as it stretches, it makes it taller. And it also makes it really skinny. That's what a vertical stretch does to a graph. It makes it taller, but it also makes it really skinny and narrow. A vertical shrink is the opposite. It's when the absolute value of a, that number in the front, is smaller than 1. So for instance, like a fraction that is less than 1. So like a half, a fourth, a third. Those are vertical shrinks. They result in the graph being short or wide. So think about again, if you squish a rubber band, it's going to make it shorter, but it's also going to make it wider. It's going to spread out and make it wider. Let's go ahead and try a couple examples. Graph y equals to the absolute value of x. So I'm going to use a table. Y equals to the absolute value of x. And stretches and shrinks are good to have tables with because they get you the actual points. My x values, I'm going to pick -2, -1, 0, 1, and 2, and plug them in. Y equals to the absolute value, -2. The absolute value of -2 is +2, and 2 times 2 is 4. Equals 2 times the absolute value of -1. The absolute value of -1 is 1, times 2 is 2. Y equals 2 times the absolute value of 0 is 0, and 0 times 2 is 0. Y equals 2 times the absolute value of 1 is 2, and y equals 2 times the absolute value of 2 is 4. Okay, so there's my order pairs. Let's go graph it. -2, 4, -1, 2, 0, 0, 1, 2, and 2, 4. Connect our dots together. Okay, so there's our new function, y equals to the absolute value of x. How does this graph compare, though, to the parent function, y equals the absolute value of x? Okay, well, it's a V shape as well. But if we think about that function, this is what the absolute value graph looked like. Looked like that going that way, and it looked like this going the other way. So you can clearly see by my picture that the new graph made the 2 in the front, made my new graph very skinny, and it's making it taller. It made it narrow and tall. And that's what the 2 did. So how it compares, you would say a vertical stretch by 2. Because of the 2 in the front, it's bigger than 1, which makes it a vertical stretch, making my green graph really tall and a bit narrower than the parent function. Domain and range, we can describe the same kind of way. Domain, forever to the left and right, so it's negative to positive infinity. Range, it still started at 0, and it went up to positive infinity. So that's our domain and range. Let's try one more. Y equals 1/2 the square root, or the absolute value of x. X, y equals 1/2 absolute value of x. And then my y values that I'm going to get out. Again, I'm going to just choose our normal 5 points that we like and plug them in. 1/2, the absolute value of -2. The absolute value of -2 is +2, and 2 times 1/2 is 1. Y equals 1/2 times the absolute value of -1. The absolute value of -1 is +1, and +1 times 1/2 is 1/2. Y equals 1/2 times the absolute value of 0 is 0. Y equals 1/2 times the absolute value of 1 is 1/2. And y equals 1/2 times the absolute value of 2 is 1. There's my list. Let's go plot them. -2, 1. -1 is at 1/2, which is like right there. 0, 0. 1, positive 1/2. And then 2 is up at 1. That's what my graph looks like. Makes that very wide V. Let's compare it to the parent function. The absolute value graph, we already did on the previous problem, looked like this, what I'm graphing right here. And it makes the same kind of shape. What do you notice, though, is the difference between the red and the green graph? Right, the red graph got wider because of the 1/2. Remember we said that is a vertical shrink by 1/2. Okay, so just know that a vertical shrink is going to make the graph wider. A vertical stretch is going to make it narrow, and it's all based on the number in the front here. If it's bigger than 1, it stretches it. If it's smaller than 1, it shrinks it and makes it wider. Okay, so some order of transformations. If I give you multiple transformations, so let's say I give you a stretch and a reflection, or I give you a shift vertically and a reflection. It's important to know which order to do things in, that way you'll end up with the correct graph. So first, you always want to do your reflection first, then do the vertical stretch or shrink. Remember, reflections based on if the x is positive or if it's where the negative is, basically. So it's based on where the x is negative. If it's on the outside, it's over the x-axis. If it's on the inside, it's over the y-axis. Vertical stretch, remember, is that number in the front. If the absolute value is greater than 1, then it's a stretch. If the absolute value is less than 1, so a fraction, then it's a shrink. Horizontal is if there's like an x plus or minus c on the inside of the parentheses. And vertical is if I have x plus or minus d on the outside of the parentheses on my function. Let's try some examples just to recap what we've done today. State the transformations. F of x equals negative x minus 3 squared plus 1. What kind of parent function does this go with? Right, the quadratic, x squared, because of the squared right there. So I can go find what my transformations were. Remember the order. First is your reflection. There's a negative out in front, so this is reflected over the x-axis. Okay. Next one's the vertical shrink or stretch, but I don't have any of those because there's just a 1 in the front. That's totally fine. Then next comes the horizontal, negative 3, tells me to go 3 units to the right. And then last one is the positive 1, tells me to go up 1 unit. Okay, now I can draw a sketch of this real quick. I know the quadratic function, its parent function looks like this. My new graph, I'm going to do exactly what it says. I'm going to reflect it over the x-axis, so now it's going to point down. I'm going to go 3 units to the right, and then I'm going to go 1 unit up. So 1, 2, 3 to the right, 1 unit up, and then draw my sketch. Reflect it, so you flip it down, go 3 to the right and up 1. Next one, y equals 2, the absolute value of x minus 5. This one is what kind of parent function? Right, the absolute value function. What does that look like? Good, it's a V shape. So our graph is also going to be a V shape. And let's take the transformations that occurred. No reflections, no need to worry about that because there's no negative in the front or with the x. No need to worry about it. Then think about the 2. What does the 2 do to the graph? Right, it's a vertical stretch because it's bigger than 1 by 2. Let's see if there's anything else. There's no left or right because it's just x on the inside. And the minus 5, what does that tell me to do with the graph? Right, go down 5 units. So let's draw a real quick sketch of what our function looks like. The parent function remembers this V shape, meets at the origin. Now I'm going to do what my graph says. No reflections to worry about. Remember the order. Next comes a vertical stretch. Vertical stretch, remember, makes the graph narrow. Tall and narrow like a rubber band. So I know it's going to be narrow. And then I'm going to go down 5 units. 1, 2, 3, 4, 5. Start at 0, 0 like the parent function says to. Go down 5 and make my graph skinny, tall and narrow.